Hello, dear students. Welcome back to the chemistry class. Today, we will continue with unit number 5, the periodic table of chemical elements, and the lesson is the second, part 2. The first part was the variation of atomic and ionic radii, and today it will be the trends in the variation of ionization energy and electron affinity. At the end of this lesson, you should be able to explain how ionization energy varies across the period and down the group, with the exceptions. And you should also be able to explain how electron affinity varies in the periodic table. And of course, if we have exceptions, you should also be able to explain them. Here we have some questions for a quick revision. You will try them. What is first ionization energy? We have studied this in unit number 2. Ionization energy, and then what is the meaning of first ionization energy? Secondly, write an equation for the second ionization of magnesium. And number 3, write an equation for the process which takes place when chlorine gains 1 electron. You will try this. And when we will be discussing, we will give the answers for these 3 questions. Here we have the trends in the variation of ionization energy. And first of all, let us have a look at the definition of ionization energy. It is the energy required to remove an electron from an atom. Here you can use or define this energy in terms of mole, and it will be the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. And metals lose electrons more easily than non-metals. You know, metals tend to lose than gaining, while non-metals will always react by gaining electrons or sharing electrons. So when metals are to react with non-metals, metals gain while the non-metals gain while the metals lose. Non-metals lose electrons with difficulty. They like to gain electrons. And then ionization energy increases across a period because the positive charge increases. The number of protons in the atom increases. We know that when you move across the period, there is a decrease in atomic radius. And that shows how ionization energy will vary. If the size is becoming smaller, then the electrons become more strongly attracted by the nucleus. And if they are more strongly attracted, then you will find them to be very difficult for being removed. So as you move across the period, ionization energy increases. You can see it on the table here. Let's consider the second period. It's here. From lithium to beryllium, it is increasing. And from boron to carbon, it increases. Nitrogen, it increases. There is an exception on oxygen. And on fluorine, it also increases. And neon, it also increases. So there is a general increase across the period. Trends in ionization energy. The ionization energy is highest at the top of a group. So what happens in a group? You can see from lithium, we have 520, sodium 490, potassium 420, and this is in kilojoule per mole. So you can see that generally it is decreasing as you move down the group. So why is it decreasing? It's because, if you remember well, the atomic radius is increasing, and as it becomes larger, it means that the electrons are being weakly attracted. When they are weakly attracted by the nucleus, they go far from the nucleus. And if they are far from the nucleus, then it will require less energy to remove them. So as you move down in a group, there is a general decrease in ionization energy because electrons are becoming less attracted, what is shown by the larger atomic radius. And the result from an effect, so this is a result from of what we call the shielding effect. Because of the extra electron which is added, sorry, the extra energy level which is added, then the shielding effect becomes stronger. When electrons are experiencing a stronger shielding effect, they go far from the nucleus, experiencing a weaker attraction, and then it becomes very easy for them to be released or to be removed from the atom. Ionization energies are periodic. You can see we have a graph here showing how the ionization energies are changing. From lithium to beryllium, it is increasing. On boron, it decreases, but when you move from boron up to nitrogen, it is also increasing. And here there is an exception. Here, let's remind that generally across the period, ionization energy increases, and generally down the group, ionization energy decreases. You can explain this by using the variation of atomic radius. You can see that from lithium to sodium to potassium, rubidium, it is generally decreasing, and across the period, from sodium to magnesium, it is increasing. Aluminium, silicon, phosphorus, it is increasing. Here we have some exceptions. For group 2 and group 5 elements, we have some abnormal behavior. The first ionization energy is very high. Why? Because the electron is removed from a full orbital. So when orbitals are full, for group 2 we have S2, and for group 5 we have P3. So for the full orbital, the electronic configuration is very stable. And for the half full orbital, the electronic configuration also is very stable. Being very stable means that it will require a lot of energy to destabilize or to remove the electrons, because you are trying to create an unstable state. So because the full and the half full orbitals are thermodynamically stable, that is the reason why the first ionization energy for group 2 is always very high compared to group 3. You can see, for example, on aluminium, we have 580 kilojoules per mole. But for magnesium, we have 730. So for magnesium, it is greater than aluminium. And that is the reason why we say there is a general increase, but we also have some exceptions for group 2 and group 5. You can see from silicon to phosphorus and sulfur, we would be expecting sulfur to have greater ionization energy than phosphorus. But phosphorus and other group 5 elements show exceptionally high first ionization energies because the electrons are being removed from thermodynamically stable orbitals, which are half full. And for group number 2, they are full. Now, let us have a look at the electron affinity. The electron affinity actually is the opposite of ionization energy. It is the opposite of ionization energy. Ionization energy, it is the energy required, which accompanies the removal of an electron from an atom. And for electron affinity, it is the energy change which accompanies the addition of an electron to the atoms. So the energy change, which occurs when 1 mole of gaseous atoms gain 1 mole of electrons, is called the electron affinity. Here we have the example of the equation involving electron affinity. You can see 1 mole of oxygen gas is gaining 4 electrons to produce 2 moles of oxygen anions. And the energy is here, which is negative 142. It is negative because the energy is released. So the process is exothermic. Trends in electron affinities. Let's analyze what we have in the table. You can see with the exception of this, of course, and we will not consider this one because these are exceptions. You remember group 2 and group 5. So let us consider lithium and boron carbon. You can see that the values are becoming more. Here we have negative 60. Here we have negative 200. Sorry, negative 27. Here we have negative 53. Here we have negative 42. So the values, as I said, they are negative because energy is released. And the value you can see for magnesium, or let's say for aluminium, what is happening? So generally, when we move across the period, we know that atomic radius increases. Now, if the atomic radius is decreasing, that's what I mean, it decreases across the period. If the atomic radius is decreasing, it shows that the extra electron which will be added will be strongly attracted. As it is strongly attracted, what happens? It will be seen that the energy that will be released when that electron is added and is strongly attracted will increase. So moving across the period, generally, electron affinity increases, with some exceptions, of course. And moving down the group, generally it decreases. You can see what happens from fluorine to, or let's say from chlorine to iodine. Negative 349, 325, 295. So the energy produced is becoming less. So here you don't have to be confused by the negative values. The negative sign here means that energy is released. So it doesn't have the same significance as in mathematics. So moving down the group, the energy is decreasing. So this shows that only 53 kilojoules per mole will be released for sodium. For potassium, it will be 48, and for rubidium, it is 47. So the energy produced is decreasing as we move down the group. But now, we have some exceptions. For group number 2, you can see that the energy is greater than that of, for beryllium, it's greater than what could be expected. So the process for beryllium or for magnesium, it is endothermic. Why? Because the orbital to which we are about to add the electron is very stable, as I said, for the ionization energy. It is the same for group number 5, where the electron to be added is about to be added to a very stable electronic configuration, half full orbital. So because of this, you have to force. And when you force, you have to supply energy. So that is the reason why the values may be less negative than what could be expected. Why? Because we have to force, we are forcing. Or sometimes it will even be positive to show that we are adding energy so that we can add that electron. So generally moving across the period, electron affinity increases. More energy will be produced when the electron is added. Why? Because the nuclear charge is increasing, the atomic radius is decreasing, showing that the electron that is to be added will be strongly attracted, and then more energy will be produced when the electron will be added. But moving down the group, generally, electron affinity decreases. Why? It decreases because we have atoms which are becoming larger. So to attract the extra electron will be not very easy. The attraction is weak, and being weak, less energy will be produced. We have an exception on fluorine and chlorine. So if we say that going down the group, the value increases, sorry, the value is decreasing. Less energy is being produced. But you can see that chlorine is producing more energy than fluorine. This is because for fluorine, we have a small size, and the very small size makes the 9 electrons. The 9 electrons we find in fluorine, they are so closely packed that they create a very strong shield for the incoming electron, hence reducing the energy that is produced. So it's because the 9 electrons closely packed in the small size of fluorine, they are creating a strong screening effect for the electron to be added. We have explained this, so down the group it decreases, and across the period it generally increases because the atomic radius is decreasing. And down the group it is because the atomic radius is increasing. We have explained this. You can see how it is varying across the period. Generally there is an increase. And for the noble gases, we don't have electron affinities. Why? Because they do not tend to react. So, and if they would have electron affinities, this could be very highly endothermic, to mean that they will be very positive because you will be required to force a lot. So we have also explained the exceptions. For the exception of group 2 and group 5, because of the stable electronic structures, the electronic configuration. Remember the full orbital and the half full orbital. So they are very thermodynamically stable, that if you have to add an electron, you have to force. We have also explained for fluorine, the reason why it has a smaller value than chlorine. And here there is another exception, or another thing to be highlighted. The second, the third, the fourth, and so on, electron affinities are always positive. And this is because, but for other, for many atoms, we have the first electron affinity, which is always negative. Energy is released when the electron is added. But for the second, it is always positive because we have a negative particle which attracts an extra electron, the electron which is also negative. So we have to force that the negative particle attracts another negative particle. We are about to combine two negative particles, so we have to force, and that is the reason why we supply energy, making it positive. Here we have some exercises, the exercises you will try, and we will share the, you will share the answers on, you will share the answers with me on Google Classroom. So explain how the first ionization energy varies in group 2. Explain how the first electron affinity varies across period 3. Why does fluorine have smaller first electron affinity than chlorine? We have seen that. And why is the second electron affinity of oxygen positive? And number last, why is the first ionization energy of magnesium greater than that of aluminum? Thank you very much. Have a good class.